Hello students, welcome to the online lecture series of St. Andrews Institute of Technology and Management, Gurugram. Myself Satendra Vats, Assistant Professor in ETC Department. In today's video, we will see the first order and second order system and their analysis. It is a part of unit 3rd of Signals and System, doubly 4th semester. Okay. So, first of all, we will see the analysis of first order and second order continuous time systems in this video. So time response analysis is a study of output with respect to time, that is how our output is changing with respect to time. Of course it will depend upon the input we are providing, but time response means how is our output changing with respect to time. So using time analysis we can study the stability of a system. It can be used to define the stability of a system, or the accuracy, how accurate our system is, and the errors in the systems, so that we can make our system efficient if we know the errors in our systems, so we can always rectify that error. So there are two types of responses in time domain analysis, that is a transient response and steady state response. So let's see what are these response. Now consider a system in which we have input as Rs, Cs as the output, Gs is the transfer function or the open loop transfer function. Open loop transfer function means when we do not have any feedback in the system, and Hs is the feedback function. So we know that transfer function is always output upon input. So in this case transfer function would be Cs divided by Rs. So it would be Gs upon 1 plus Gs Hs, which is the case for positive feedback, negative feedback. So this is Gs upon 1 plus Gs Hs, where Gs is the open loop transfer function if there was no feedback, and Hs is the feedback function. So Cs now becomes, if I put the value of in this equation, that is Cs is equal to Ts into Cs now is the transfer function into input function Rs. So it becomes Cs is Rs multiplied by Gs upon 1 plus Gs upon Hs. Okay. So now take the inverse Laplace transform of that equation. We will get Ct as Laplace inverse of Rs into Gs upon, if I take this function's Laplace inverse, then I will get the Ct. So you can always, depending upon the Gs and Hs values, you can solve this function to get the function output in time domain. So if let's say example, this is a randomly taken example, if this is our output Ct with respect to time, so till this point it is increasing with time. So this response is called the transient response till the output of the system is changing with time, and after this time period our output has now stabilized, it is not changing with the time. So this is called the steady state response of the system. Okay, so these are two types of responses, transient response and steady state response, when our system output now has become stabilized. So first of all, see now the unit step response for a first order system. So first transfer function for a first order system can be given as 1 upon 1 plus st, because the power of s is 1 in this system. So it is the first order system. Rs is our input and Cs is our output in Laplace transform or frequency domain, and Rt and Ct are the input and output respectively in time domain. So now let's say our inputs to the system is a unit step, that is ut, which is 1 for t greater than 0 and 0 for t less than 0. So Laplace of unit function is 1 upon s. Okay, so Cs, this Cs in the first order system is Rs into transfer function, that is input into transfer function. Input is 1 upon s and transfer function is this one. So this is our output in frequency domain. So now using partial fraction I have split this function in two terms, that is 1 upon s minus t upon 1 plus st. So using partial fraction you can do that. Now so Cs is now become 1 upon s minus 1 upon s plus 1 upon t. If now I will take the inverse Laplace transform, this is for ut, that is I will get ut, and this is for e raised to power minus at ut. So in this we get e raised to power minus t, a is 1 by t. So e raised to power minus t by t into ut. So this is how I can get the output in time domain using inverse Laplace transform. So taking ut common, I get ut into 1 minus e raised to power minus t by t ut. So this is our response or the output for the unit step. So if I draw this, it would come out to be like this. It would become 1 at infinity. So at t, if I calculate the amplitudes of this output at time t, it would be 0.63, one of the highest amplitude, that is 1. 0.63% or 63% of highest value at time t. At 2t it will become 86.5%, at time 3t it will become 95%, and at time 4t it will become 98.2% of the final value. So this is our response of the system, first order system, to a unit step signal. Now let's see the response for a unit ramp signal of first order system. So again this is our first order system in which the open loop transfer function is 1 upon st and negative feedback is 1. So the closed loop transfer function will again come out to be 1 upon 1 plus st as in the last example. So Cs would become Rs into 1 plus 1 upon 1 plus st as in the last example, but here Rs is a unit ramp. So for unit ramp, the Laplace transform of unit ramp, that is t is equal to 1 upon s square. This is unit ramp, that is rt is equal to t, and its Laplace transform is 1 upon s square. So putting these value in this equation, I get 1 upon s square plus into multiply 1 upon 1 plus st. Using partial fraction I calculate, it comes out to be this 1 upon s square minus t by s plus t into 1 upon s plus 1 by t. If I will take the inverse Laplace transform of this function which I have calculated using partial fraction, I have split it into 3 parts. So it comes out to be Ct is equal to t minus capital T plus t into e raised to power minus t upon capital T. So if I say in this diagram, you can see if this is our Rs or RT, this is our output. If I'll take the feedback that is here, so our error signal would be RT minus, it would be RT minus CT. That is the difference between the input and output signal. This is our error signal. So when I calculate it, it comes out to be t minus t e raised to power minus t by t. So steady state error means when the system's output becomes stabilized at t is equal to infinity. So steady state error can be calculated as limit t tends to infinity, that is time tends to infinity in this function et. So it comes out to be capital T. So if this is our input, that is a ramp signal, and this is our output for this function, then this difference is the error signal. Okay, so differential equation for a first order system is given by, we have seen that the unit step response and unit ramp response for a first order system. Now we can also see that the differential equation for a first order system can be write as this one, that is capital T into dy by dt, that is a first order differential, plus yt is equal to xt, where yt is the output and xt is the input. So its transfer function will come out to be ys upon input xs, that is hs, or ts is equal to 1 upon st plus 1, which we have used in the previous example. So this is the first order differential equation, which we can calculate using the inverse Laplace transform and Laplace transforms, or we can use Fourier transform as well. So now comes the second order systems, in which we will use second order differentials, that is d square yt by dt square plus 2e omega n dyt by dt plus omega n square yt is equal to omega n square xt, where xt is the input. So when I calculate using the Laplace transform, the transfer function of this differential equation or the system comes out to be, for a second order system, ys upon xs is equal to hs or ts is equal to omega n square upon s square plus 2e omega ns plus omega n square. So this is the transfer function for a second order system, in which omega n is the natural oscillation frequency of our system, and that E is the damping factor or damping ratio. So if hs is our transfer function, rs or rt, sorry, this is rt is our input, and cs and ct are our output in frequency and time domain respectively. So cs can be written as rs into hs, that is input into transfer function. So if we are using the unit step, then the rs would be 1 upon s, and this is the transfer function. So this system can be characterized on the basis of the roots of this equation, that is the denominator of transfer function, that is s square plus 2e omega ns plus omega n square. So we can characterize our system using these equations, whose roots comes out to be that is minus b plus minus under root b square minus 4ac divided by 2a. Using this formula we can calculate the roots, which comes out to be s1 s2 is equal to minus 2e omega n plus minus square root 4e square omega n square minus 4 omega n square by 2. So these are two roots. Okay, so s1 and s2 can be rearranged as this one. So s1 and s2 are comes out to be minus e omega n plus minus omega m under root or omega n e square minus 1. So there would be 4 cases for this. If e is equal to 0, then the roots s1 and s2 will be imaginary, that is plus minus j omega n, and our system would be underdamped. Okay. For case second, e is equal to 1, that is the roots will be minus e omega n, that is real and repetitive. So system is critically damped in this situation. Case third, when e is in between 0 and 1, so roots will come out to be complex, that is minus e omega n plus minus omega n under root e square minus 1, which is the real and imaginary parts. So the system would be underdamped. Sorry, in first case it was undamped. There was no no oscillation or undamped or with the natural frequency. Okay, but in case third it is underdamped with complex roots. And one more case is possible, that is for e, that is the damping factor or damping ratio greater than 1. So in this case, two roots would come out to be minus e omega n plus minus omega n under root e square minus 1, that is real and distinct root. So for e greater than 1, we will be having a distinct root and our system will be over damped. So for e is equal to 0, it will be undamped. For e is equal to 1, it will be critically damped, and for e between 0 and 1, it will be underdamped, and for e greater than 1, it will be over damped. So let's see in a diagram. So this would be the second order response for a unit step, that is ut. I have used the unit step in the solution, so it can change if I use a ramp signal or a parabolic signal. So this is our e is equal to 1. Okay, and as the value of e is decreasing, we are getting more fluctuations in our signal. And for E greater than 1, that is 1.5, we are getting a overdamped signal. Okay, for E is equal to 1, it is critically damped, and for the value E less than 1 or greater than 0, it will be underdamped. Okay, so this is the response of a second order systems. So in your exams, university exams, it comes explain the solution of a second order system. So you need to do all these things, and if it comes for a first order system, you can describe it using a unit step signal or a ramp signal, or you can use the parabolic signal as well. So this is it for this lecture, in which we have seen the analysis of first order and second order systems using the what we have used in this analysis is Laplace transform, or we can use it using Fourier transform as well. Okay, because Fourier transform becomes Laplace transform, or we can say Laplace transform become Fourier transform for s is equal to j omega. So we can use any of them. Thank you very much.